The world of science has a few bedrock rules. They're called the laws of thermodynamics. They govern energy, heat, and work. They explain why your coffee gets cold and why you can't build a perpetual motion machine in your garage. For over a century, we've been comfortable with them. There were three, plus an extra one they added later and called the Zeroth Law, just to be neat. The Zeroth Law is simple. If a cup of coffee is the same temperature as a donut, and the donut is the same temperature as a plate, then the coffee is the same temperature as the plate. It's the no-duh law of temperature. It just says things in contact eventually reach a shared temperature. The first law is famous. Energy cannot be created or destroyed. It only changes form. The chemical energy in a log becomes heat and light when you burn it. The total amount of energy in the universe is constant. You can't win. You can't get something for nothing. The second law is the most profound. It's about entropy. Entropy is just a word for disorder or randomness. The second law says that in a closed system, entropy always increases. Things fall apart. Your organized bedroom gets messy. A hot cup of coffee cools down, its heat spreading out into the room. The universe is constantly moving from a state of order to a state of disorder. This law is why time seems to move forward. It's the great cosmic downer. It says you can't even break even. The third law is a bit more obscure. It says you can never reach absolute zero. That's the coldest possible temperature, where all atomic motion stops. You can get really, really close, but you can never actually get there. It's the universe telling you that you can't quit the game. These laws were it. They were the foundation of physics, chemistry, and engineering. They were solid, unquestionable. We built our entire industrial world on them. And then, everything changed. It didn't happen with a bang. It happened in a quiet lab, with a team looking at data from a new space telescope and running simulations on a supercomputer. They weren't looking for a new law. They were studying the formation of complex structures in the universe, like galactic superclusters. At the same time, a different group was modeling the information flow in biological ecosystems. Another was analyzing the fragility of global financial networks. All three teams, working independently, hit the same wall. Their models kept breaking down in a weird way. When a system, be it a cluster of galaxies, a rainforest, or a stock market, reached a certain level of interconnectedness and complexity, it didn't just get slow or inefficient. It became brittle. It would suddenly and catastrophically collapse into a much simpler state. At first, everyone thought it was a bug in the software, or bad data, but the pattern was everywhere. A star system with too many intricate orbital resonances would fly apart. A rainforest ecosystem with too many specialized species would suffer a total collapse from a small change. And artificial intelligence that was given too many layers of self-referential logic would descend into a kind of digital dementia. The paper that finally put it all together was unassuming. It was titled, "On the Upper Bound of Systemic Complexity." It didn't grandly announce a new law of the universe. It just presented the data and a terrifyingly simple conclusion. It proposed a fourth law of thermodynamics. The law, when translated from the math, said this: any system can only sustain a certain level of complexity before it becomes inherently unstable. Beyond that point, the energy required to maintain the complexity exceeds the energy available to the system, and it will spontaneously simplify, often violently. Think of it like a Jenga tower. Each block you add makes the tower more complex, taller, more impressive. But each block also makes it more unstable. At some point, you add one block too many. The whole thing doesn't just lean, it collapses into a simple pile of blocks on the table. The fourth law said that this wasn't just a fun party game. It was a fundamental rule of the universe. The initial reaction from the scientific community was brutal. It was dismissed as a statistical error, a misunderstanding of information theory. But the evidence kept mounting. Physicists re-examined old data and saw it. Biologists looked at the fossil record and saw it in mass extinctions. Economists looked at historical market crashes and saw it there too. After a decade of furious debate, replication, and argument, the consensus shifted. It was real. We had a new law. And the world began to feel very different. The first and most immediate impact was on technology, specifically on the development of artificial intelligence. For decades, the goal was to build bigger, more complex neural networks. We believed the path to true consciousness was through more processing power, more data, more intricate algorithms. The fourth law put a hard stop to that. It suggested that a truly super intelligent AGI might be a physical impossibility. As a research AI approached the complexity limit, it wouldn't become a god. It would become unstable. Its logic would fray. It might start making beautiful but nonsensical connections. It could get trapped in infinite loops of self-analysis, or it might just crash into a simpler, dumber version of itself. The problem of AI safety was no longer just about controlling its superintelligence. It was about preventing our creations from reaching a level of complexity that would cause them to self-destruct, possibly taking our interconnected world with them. The race for AGI became a race to find elegance and efficiency in simpler systems, not a brute force climb toward infinite complexity. The internet felt the chill of the new law, too. Our global network of information was seen as a monument to human ingenuity. But now it looked like a Jenga tower in the middle of an earthquake. The sheer number of connections, the speed of information, the layers of social networks, financial systems, and logistical chains built on top of each other. It was a system of unprecedented complexity. The fourth law suggested that it wasn't resilient, it was fragile. A single, well-placed shock might not just disrupt it, it could trigger a complexity cascade, causing the entire system to simplify. What would that look like? Maybe a collapse of global finance, a breakdown of supply chains, a fragmentation of the internet into smaller, isolated networks. We started to see that making everything smart, and connecting it all together wasn't necessarily progress. It was adding blocks to the tower. This new understanding trickled down into engineering and city planning. For a century, the trend was towards bigger and more centralized systems, giant power grids, massive water supplies, continent-spanning transportation networks. The fourth law showed the hidden danger in this approach. These systems were efficient, but they were also incredibly complex, and therefore incredibly fragile. A failure in one part could bring the whole thing down. The new philosophy became resilience through simplicity. Decentralization became the goal. Instead of one massive power grid, the focus shifted to microgrids for individual communities. Instead of global supply chains for everything, there was a renewed push for local manufacturing and food production. The idea was to have many simple, robust systems instead of one complex, brittle one. If one local system failed, the others would continue to function. It was a retreat from the grand, interconnected dream of the 20th century. It was an admission that too big to fail was a myth. The truth was that some things were too complex to succeed. Biology was turned on its head. The second law explained why organisms had to constantly consume energy to fight against decay and disorder. The fourth law explained why they had to fight against overcomplication. Evolution wasn't just a march towards more complex and sophisticated life forms. It was a delicate dance on the edge of the complexity limit. Mass extinctions were reinterpreted. The asteroid that killed the dinosaurs was the trigger, but maybe the global ecosystem was already at its complexity limit. It was so intricately interconnected, so full of specialized predators and prey, that it was brittle. The asteroid was just the finger that flicked the Jenga block. A simpler, more robust ecosystem might have survived the impact better. This gave us a new appreciation for the primitive organisms that have survived for billions of years, like bacteria and algae. They aren't failures of evolution, they are its greatest successes. They are masters of simplicity and resilience. They operate far from the complexity limit, which is why they can survive almost anything. Our own bodies were seen in a new light. The human brain is the most complex object we know of. The fourth law made us wonder how close we are to the edge. It offered a potential physical explanation for things like mental breakdowns under extreme stress, or the eventual decline of cognitive function in old age. Perhaps these weren't just biological wear and tear. Perhaps they were small, personal encounters with the fourth law, a system reaching its informational limit and beginning to simplify. But the most profound changes weren't in our technology or our science. They were in our philosophy, our politics, and our sense of who we are. The story of humanity, especially in the Western world, had been one of endless progress. We believed we could always grow, always build bigger, always get smarter, always solve any problem by adding another layer of technology or bureaucracy. The fourth law was a direct contradiction to that belief. It placed a fundamental physical limit on our ambitions. It said that our global civilization, with its tangled web of economies, cultures, and technologies, was not on a path to a glorious, unified future. It was on a path to a complexity cliff. The constant drive for more economic growth, more globalization, more interconnectedness was pushing us closer and closer to the edge. This created a deep schism in politics and economics. On one side were the complexitarians, who believed that with careful management and new technology, we could push the limit further, or even find ways around it. They argued for more powerful AI to manage our systems, for global governance, for a more integrated world, believing that we could master complexity itself. On the other side were the simplifiers. They saw the fourth law as an urgent warning. They argued for degrowth, for breaking up large corporations and nations, for a return to local communities and simpler ways of life. They believed the only way to avoid a catastrophic collapse was to voluntarily step back from the brink to consciously reduce the complexity of our civilization. Their motto was, "Simple is safe." This debate wasn't academic. It colored every political decision. Should we build a new global communication network? The complexitarians said yes, it would increase efficiency. The simplifiers said no, it would add another layer of dangerous fragility. Should we merge two multinational banks? The complexitarians saw economic benefits. The simplifiers saw a concentration of risk that pushed the entire financial system closer to its collapse point. The law also changed how we saw ourselves. The idea of progress had been our secular religion. It was the belief that our children would have a better, more advanced life than we did. The fourth law suggested that this might not be true. It suggested that a better life might actually be a simpler one. It introduced a cosmic humility into our culture. We weren't the masters of the universe destined to conquer the stars. We were a complex system born on a small planet, subject to the same fundamental rules as a star cluster or a yeast colony. And, like them, if we got too big for our britches, we would fall. This was a hard pill to swallow. For many, it led to a kind of despair, a new cosmic pessimism. If the second law told us we were all doomed to heat death in the distant future, the fourth law told us our own civilization could be doomed to collapse in the very near future, brought down by its own success. But for others, it was liberating. It freed them from the relentless pressure to grow, to innovate, to complicate. It gave them permission to seek value in things that were small, local, and resilient. A new kind of environmentalism was born, one that focused not just on pollution or climate change, but on complexity pollution. It argued for preserving not just biological diversity, but also systemic simplicity. We started looking at history differently. The fall of the Roman Empire, the collapse of the Mayan civilization, the Bronze Age collapse, were these just historical events driven by politics and climate? Or were they textbook examples of the fourth law in action? Civilizations that grew too complex, with supply chains that were too long and bureaucracies that were too layered, until a small shock, a famine, an invasion caused the entire brittle structure to shatter into a simpler, darker age. Our history wasn't a story of linear progress. It was a cycle of rising complexity followed by sudden, sharp simplification. This new law gave us a new lens through which to see the universe. We looked up at the night sky. The second law told us that the stars were burning out, that the universe was winding down. The fourth law added a new chapter to the story. It said that the universe's journey into darkness wasn't just a slow fade. It was punctuated by collapses. A galaxy, over billions of years, might develop intricate gravitational relationships, its stars and nebulae weaving a complex cosmic dance. But if it became too complex, it might undergo a period of violent instability, ejecting stars and simplifying its structure before continuing its slow march towards heat death. The fourth law was a mirror. It showed us that the same rule that governed the fate of galaxies also governed the fate of our internet, our economies, and maybe even our own consciousness. It connected the largest scales of cosmology with the most intimate aspects of our lives. We live in the world of the fourth law now. It hasn't stopped us from exploring or learning, but it has changed the direction of our gaze. We no longer just look up towards bigger and more complex futures. We also look down at the foundations, seeking to build things that are not just powerful, but durable. Not just smart, but wise. The coffee on my desk is still getting cold, a perfect demonstration of the second law. The energy from my lamp is a conversion from electrical to light and heat, a nod to the first law. And the temperature of the mug is the same as the desk it sits on, a quiet hello from the Zeroth. But now there's a new thought. I think about the computer I'm typing on connected to a global network of billions of other computers, a system of such staggering complexity that it makes me nervous. But I think about the tower I'm building with my words, and I wonder how many more can I add before it falls. The fourth law of thermodynamics doesn't give an easy answer. It just tells us that the question is real and that we should ask it about everything we build. It's the universe's way of telling us to be careful. The fall is a long way down.